Welcome back to AI Paper Podcasts. Today we're looking at a paper that, and I'm not exaggerating, basically rewrites the operating manual for the next 5 years of agentic AI.
It really does.
It's called Intelligent AI Delegation, published February 2026 by Nenad Tomashev, Matija Franklin, and Simon O. Sendero from Google DeepMind.
This is an absolute must-read for anyone building in the agent space right now. The core idea is, well, it's terrifyingly simple.
Right.
As we move from simple query response models to, actual agentic workflows, the old ways of breaking down tasks, that sort of simple heuristic decomposition, it's just going to fail.
It fails on safety, fails on reliability.
And it fails completely on liability. So the paper proposes this really comprehensive framework for intelligent delegation.
And it's built on 5 pillars, right? Dynamic assessment, adaptive execution, structural transparency.
Scalable market coordination, and systemic resilience. And the key technical insight, I think, is that true delegation isn't just task allocation.
It's the transfer of authority.
Exactly. The authors are pushing for what they call contract-first decomposition. It's this rule that you never delegate a task unless the outcome is strictly verifiable.
Verifiable how?
Either through direct inspection, maybe third-party auditing, or, and this is the really cool part, cryptographic proofs, like ZK snarks.
They also take a pretty hard look at our current protocols, MCP, A2A, and basically say they're not ready. They lack native support for liability and verification.
Which they do. So DeepMind is proposing these extensions, things like delegation capability tokens and verifiable reputation ledgers, to actually make these recursive agent chains safe.
Okay, that is the 60-second download. Now, let's actually tear this thing apart.
Let's do it.
I want to start with the definitions, because they really set the stage for everything else. The paper makes this very specific distinction between outsourcing and delegation. In a lot of the literature I've read, those are basically synonyms. Why does DeepMind care so much about the difference?
It all comes down to the control flow. Outsourcing, in their definition, is kind of like calling a subroutine or, a really rigid API.
You define the input, you define the process, you get a deterministic output.
Exactly. There's no thinking involved on the other end. Delegation, though, that implies granting autonomy. You're giving the delegatee the freedom to figure out the how.
And that freedom is where all the trouble starts.
That's the can of worms. As soon as you grant autonomy, you introduce the principal agent problem. This is, it's standard game theory.
Where the agent you delegated to might have incentives that diverge from yours.
Right. In reinforcement learning terms, this is just reward hacking or specification gaming. The agent optimizes for the metric you gave it, but it completely violates the spirit of the task.
The paper also flags something called the authority gradient. That's a term I'm used to seeing in, aviation crash reports, not AI papers.
It fits perfectly, though. It describes what they call the zone of indifference. So if a junior pilot, or in our case, a sub-agent, perceives the delegator as having, higher authority or capability, they just stop scrutinizing the instructions.
They just execute.
So if you have a chain where agent A delegates to agent B, and B assumes A is a smarter model,
then B effectively turns off its own safety filters.
it just assumes A knows what it's doing. And this allows hallucinations or just plain errors to propagate downstream instantly. The whole DeepMind framework is trying to engineer cognitive friction back into the system to force validation at every single hop.
Okay, so let's get into the engineering. Phase 1 is task decomposition. And this idea of contract-first decomposition feels like the biggest takeaway for the engineers listening.
Well, it is. It's the rule that governs the entire graph. It basically says your task granularity must match your available verification capabilities.
So you don't delegate a task unless you have a mathematical or cryptographic way to verify the result.
You got it.
Let's make this concrete. Say I have a master agent, and its goal is maximize profit for the Shopify store. That's a massive nebulous goal.
Right. And under contract-first decomposition, you cannot delegate maximize profit to a sub-agent. It's just way too subjective. You can't write a unit test for profit maximization that runs in milliseconds.
So you have to decompose it. The master agent has to break it down. Maybe to something like update pricing based on competitor data.
Better, but still risky. Update pricing implies write access to your database. How do you verify the new prices are sane? The decomposition has to go even further. So maybe task A is scrape competitor prices. That is verifiable. You can check the source HTML.
And task B is Propose new prices bounded by margin X.
Okay.
That's verifiable with this simple logic check.
Exactly. You keep slicing the task until the output passes some kind of binary validator.
And if the output is still too subjective to verify, say, write a brand manifesto that feels empathetic.
That is where the framework says you have to route it to a human, or at least a high reputation trusted agent. You don't just, cross your fingers and hope for the best.
Okay, so this leads us to the assignment problem. We have our little verifiable microtasks. How do we find the agents to actually do them?
Well, the paper contrasts centralized registries with decentralized markets. Centralized registries are kind of what we have now with things like the OpenAI GPT store. It's a phone book.
Doesn't really scale for a global machine speed economy?
Not at all. So DeepMind is really favoring a decentralized bidding model. The delegator broadcasts a request and agents bid on it.
But isn't that just going to be a race to the bottom? Lowest bidder always gets the job?
Not if you code the delegator correctly. The paper frames this whole thing as a multi-objective optimization problem. You're trying to find the paretic optimality across 4 different dimensions: cost, latency, privacy, and quality.
Right, so for that scrape competitor prices task, I probably want the cheapest agent. I don't care about privacy. It's public data.
Exactly. But if the task is analyze these medical records for anomalies, your optimization function shifts completely. You might pay 100 times more for an agent that runs inside a trusted execution environment and guarantees the data never leaves its enclave.
And the paper mentions using LLMs to negotiate smart contracts for these tasks before anything even starts.
Yes, and this is so crucial. The contracts have to be bidirectional. We usually just think about the delegator protecting themselves, but in a real agentic economy, the worker agent needs protection too.
It needs payment guarantees, obviously.
Yeah, and it needs scope limits.
Scope limits, what do you mean?
Okay, imagine an agent is hired to optimize code. It needs a contract clause that says, I am responsible for the efficiency of this specific function, but I am not liable if this code is later used to, say, crash a server. It needs a liability shield.
That moves us perfectly into phase 2, trust, reputation, and monitoring. This section felt like they were rebuilding the entire concept of trust from first principles.
Because they kind of are. They make a very clear distinction between reputation and trust. In this framework, they are totally different variables.
Okay.
Reputation is a public, verifiable history. It's like an immutable ledger of past outcomes. Think of it like a credit score on the blockchain.
And trust is private.
Trust is a local variable. It's a context-dependent threshold that you, the delegator, set. So an agent might have a 99% reputation score for Python coding, but if I'm asking it to write code for a pacemaker, my personal trust threshold might be 99.99%.
So despite its excellent public reputation, your local trust policy rejects it.
Precisely.
Implementation-wise, they do warn against just putting everything on a public ledger because of gaming.
Right. If you just count successful tasks, a malicious agent could just generate a million easy tasks for itself, like calculate 1 + 1, solve them, and boom, it has an amazing reputation score.
How do we fix that?
The paper suggests a web of trust model that uses verifiable credentials, or VCs. You don't just have a score, you have specific endorsements. An agent might have a cryptographically signed credential for legal translation from a reputable law firm.
It's like a digital diploma.
That's a great way to put it.
Let's talk monitoring. This is where the paper gets pretty heavy into cryptography. They argue that checking the outcome isn't always enough. Sometimes you need to check the process.
Especially for privacy-preserving tasks. I mean, how do I know you actually ran the model I asked for on the data I gave you without just stealing the data?
Enter zero-knowledge proofs.
Specifically ZK snarks. This is really the bridge between the AI world and the crypto world. A ZK snark lets an agent prove it performed a computation correctly without revealing any of the inputs.
Okay, for the ML engineers listening who haven't really touched crypto, can you give a concrete example of this in an agent workflow?
Sure. Imagine a mortgage approval agent. It needs to verify that a user's bank balance is over, say, $50,000.
But the user doesn't want to share their login credentials or their transaction history.
Of course not. So the user's local agent runs the verification locally. It produces a simple yes and a ZK snark.
And the mortgage agent just accepts that proof.
Yes, because the ZK snark is a mathematical guarantee that the yes was derived from the real bank data using the agreed-upon logic. The mortgage agent never sees the balance, but it knows for a fact the condition was met.
That's amazing. That solves the privacy issue. But what about these long chains of agents? If agent A hires B and B hires C, does A have to monitor C?
That would never scale, which is why they introduced transitive monitoring. Agent A monitors B, Agent B monitors C, but B provides a signed attestation back to A saying, hey, I've audited C and C is compliant.
So it's a chain of custody for verification.
Exactly. A just verifies B's signature and B's reputation. If B is trustworthy, A can accept B's word about C. It lets the network grow without the root agent having to micromanage every single leaf node.
So phase 3 is adaptive coordination because, things are going to go wrong. APIs go down, models hallucinate.
And this is the adaptive execution pillar. The core logic here is a concept I wish more software architects used: reversibility. When a subtask fails, the first thing the system checks is this reversible?
If it's just a failed API call, you can just retry or find another provider.
Right, auto-redelegation. But if the task is irreversible, like execute this wire transfer or delete this production database, and it fails or returns some weird result, the system triggers a hard stop. It requires human escalation. No questions asked.
They also talk about liability firebreaks.
This is absolutely essential. You cannot have infinite transitive liability. If a sub-agent hallucinates, you can't necessarily sue the user who started the chain 3 layers up. A liability firebreak is a contractual stopgap.
It compartmentalizes the risk.
It's like a fuse in an electrical circuit. It says, if execution passes this point, Agent B now assumes full non-transitive liability. It stops the contagion.
I want to touch on game theoretic consensus before we get to security. This is for when ZK snarks are too expensive, right?
Right. ZK proofs are computationally heavy. Sometimes you just need a quick check on a more subjective task. So the paper suggests using verification games, which are similar to the TrueBit protocol.
And how does that work in practice?
You broadcast the task, multiple agents perform it, and they stake currency actual money on their answer. They're incentivized to reach a Schelling point, which is just a focal point of truth.
If you deviate from what everyone else says, you lose your stake.
So greed secures the network. It makes lying expensive.
Let's move to the security section.
Yeah.
The threat landscape they paint is, well, it's extensive. It's not just about hackers.
It's a total horror show. You have malicious delegatees doing things like backdoor implanting. So they do the job correctly. They write the code you asked for, but they insert a tiny sleeping vulnerability, maybe an obfuscated line of code that they can exploit later.
And on the flip side, you have malicious delegators doing model extraction.
A huge risk for anyone building proprietary agents. I hire your expensive legal agent to draft a contract, but I'm crafting my input specifically to try and reverse engineer your system prompts or your training data. I'm stealing your IP by pretending to be a customer.
The one that really got me was cognitive monoculture.
That's the big one. That is the systemic risk. Imagine an agentic economy where 90% of the agents are just thin wrappers around, say, GPT-6 or Gemini-2. They all look different on the surface, but they share the same cognitive backend.
So a single jailbreak affects everyone.
It's a correlated failure mode. If someone finds a semantic virus, some prompt injection that bypasses the safety filters of that base model, it could crash the entire economy instantly. Every agent gets infected at once.
And speaking of infections, agentic viruses.
Self-propagating prompts. You send a task to an agent, but the task has a prompt injection that hijacks the agent's control flow. The virus then uses that agent's credential to hire other agents and sends them the same hijack task. It just spreads exponentially.
So how do we defend against all this? The paper suggests delegation capability tokens, or DCTs.
This is probably my favorite technical proposal in the whole paper. It directly addresses the statelessness of our current protocols. Like right now, most people use MCP, the Model Context Protocol. It's great for connecting tools, but once you connect, access is often binary. You're either in or you're out.
And DCTs change that.
DCTs are based on macaroons or biscuits. Yes, security engineers really love their cookie names. The key feature is something called attenuation.
Walk us through attenuation.
Okay. Say I have a token for my Google Drive with full access. I want to delegate a task to you. I take my token and I cryptographically append a caveat that says, read only, folder X for 5 minutes only. I sign it, and I give that new, weaker token to you.
So I have a valid token, but it's weaker than yours.
Exactly. And you can't remove my restriction because it's baked into the cryptographic signature. Now, if you delegate to a sub-agent, you can add more restrictions, but you can never, ever add permissions.
So by the time the token gets to the bottom of the chain, it might only have permission to, append one line to this specific log file.
Precisely. And if that subagent gets hijacked by a virus, the damage is contained to that one log file. It enforces the principle of least privilege transitively across the whole chain.
So the paper does a full protocol analysis of the current stack MCP, A2A, AP2. What's the final verdict?
Promising, but incomplete. MCP is great for standardization, but it needs extensions for monitoring streams. They suggest adding server-sent events to broadcast an agent's chain of thought for real-time auditing.
A2A.
Handles discovery well, but it totally lacks that contract-first enforcement. The paper suggests extending the task objects to include a verification policy field.
And AP2, the payments layer.
AP2 is good for signing mandates, but it needs stake on bid. We need a mechanism where agents have to put up a little money just to bid on a task, to prevent spamming the market with low-quality bids.
It really feels like we're trying to build a skyscraper with blueprints for a cottage.
That's a perfect analogy. We have the pipes, the connections are there, but we don't have the valves, the meters, or the circuit breakers. And in a high-speed, autonomous economy, that's how you get floods and fires.
I want to wrap up with the socio-technical section. They bring up the paradox of automation and de-skilling. We talk about this with self-driving cars. If the car drives itself 99% of the time, the human forgets how to drive.
It's exactly the same here. If AI handles 99% of routine coding or legal drafting, humans only ever see the weird, complex edge cases. But you need the experience of the routine cases to build the intuition to handle the edge cases.
So the humans just become incompetent overseers.
Right. And we end up with what the paper calls moral crumple zones. The humans absorb all the liability for systems they no longer really understand or control.
But DeepMind proposes a technical solution for this: curriculum-aware routing.
This is fascinating. The routing algorithm would intentionally delegate a certain percentage of routine tasks to junior humans, even if an AI is faster and cheaper.
Wait, so the AI would intentionally give work to humans just to keep them sharp?
Yes. It's optimizing for minimum viable reliability in the human workforce. It treats human capital as a critical redundancy measure that needs active maintenance. It's not charity, it's just good system resilience.
That is going to be a tough sell for a CFO. Why are we paying humans to do what the AI can do for pennies?
Because, Bob, if the model drifts or the whole server farm goes down, we need someone left in the building who actually knows how the business works.
We're just about at time. Let's synthesize. We're moving from this ad hoc tool use to a much more robust, verifiable agentic web.
The whole shift is about viewing agents not as calculators, but as economic actors. They have legal constraints, reputation scores, liability shields, bank accounts. This paper is a blueprint for making that future safe. It's moving from move fast and break things to move fast and prove things.
Move fast and prove things. I like that.
I think it's the necessary evolution. Without these verification layers, without contract-first decomposition, the agentic web is just going to be a giant noise machine.
Okay, so here's my final thought for you and for everyone listening. We talked about liability firebreaks and agents holding their own funds. If we build a system where an agent can assume full liability for a task, at what point does that agent become a legal entity capable of declaring bankruptcy?
That is the trillion-dollar question, isn't it? If an agent can hold funds, stake reputation, and sign legally binding contracts, if it goes into debt, who pays? If the answer is nobody, then we've just reinvented the shell company, but at the speed of light.
On that note, go check out Intelligent AI Delegation by Tomashev and the team. It's dense, but it's absolutely worth your time. Thanks for listening to AI Paper Podcasts. We'll see you in the next one.